Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Kiyoshi Masui with us today. Hi, Kiyo.
Hi, how's it going?
Good. It is 2022. It's January 4th as we record this one. So happy 2022 to you.
Thank you very much. Very happy to be here.
Yeah. Well, thanks for agreeing to talk about your really lovely APJ supplement article. Kiyo, where are you located at?
Right now, I am in near Boston, in Arlington. Enjoying the brisk weather outside, but no snow yet.
No snow yet. No, goodness. Okay. Well,
no, all the snow's in Vancouver apparently. I have family there, and they've got inches and inches of snow, which is weird for them.
Yeah. Okay. Something about climate, but we'll let that go. That's a pretty awesome chalkboard behind you. Looks like it's actually used at some point. You got a picture? Is that you there?
No, this is my son. The chalkboard gets used occasionally, not for technical work, mostly just for to-do lists and doodles. But
yeah, we all have our method, whether it's chalkboard or a piece of paper or whatever. It's all good. Very cool. Very cool. So yeah, I'm in Phoenix on this January 4th. It was a relatively chilly 32 this morning, right about freezing, but we'll warm up to about 65 today. So it'll be a nice day today. So let's go ahead and get to it. And Kiyo, what do you like to do for research?
Yeah, so I'm a radio astronomer, and in particular, I work with really wide field surveys, which is what I'll talk about now. So these instruments that are enabled by modern technology that can see big parts of the sky at once and do things like cosmological surveys and transient surveys.
Cool, very nice. And that is going to bring us to this very lovely APJ supplement article, the first Chime FRB Fast Radio Burst Catalog. And Kiyo, take us away.
Yeah, so this is it's really sort of the culmination of a big instrumentation effort to make wide field telescopes chime sensitive to what are called fast radio bursts. So fast radio bursts, they're these fairly recently discovered flashes of radio lights. They're millisecond long transients. That we see all over the radio sky. They are now known to be extragalactic in origin. And because they're only a millisecond long, they have to be coming from a compact object. But there's not a whole lot more that is known about them beyond that. We've been putting together a lot of clues in the last couple of years, but really they still are kind of this mysterious thing.
Indeed.
And so we've only really known about them for just over a decade now. So 2007 was the first one that was discovered using the Parkes telescope. And this is and now we're just entering the era where we can talk about not single fast radio bursts or one or two being seen in a year, but really hundreds seen in a single survey, which makes this which just changes the game for how this field can go forward.
Absolutely.
So yeah, I guess I'll start. I want to show a picture of the Chime Telescope to just say what is the technology that enabled this fast radio burst catalog. So Chime, as you can see here, is a radio telescope. But it sort of relegates a lot more of its sort of functionality to software and than most other telescopes. So it has all these reflectors. You see these cylindrical reflectors here, right? So it does focus light, but it only focuses light in the east-west direction. It doesn't bother focusing it in the north-south direction. So that means we have a really big field of view. We see basically horizon to horizon in the north-south direction. Yeah. And then just a degree-wide strip of the sky in the east-west direction in RA. And what that does for us, so that's a big field of view, right? So it's a 200 square degree field of view. And then all the spatial information we get within the field of view is all digital. That happens through interferometry or seen another way through beamforming. So we can have this, multi-pixel radio camera that sees a large swath of the sky. And there's no moving parts, right? So we can't point the telescope anywhere, but because we see the whole, see from horizon to horizon, the north-south direction, we survey a full sky as the Earth rotates. Cool. So that's how CHIME works, and it's that very digitally driven design that's really made us able to survey the sky and capture more of these fast radio bursts than any other instrument.
Nice. Nice.
So we go to figure 1, we can get to the punchline right away, okay. Which is,
and I'm going to do a little blow up here, bump, 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 and figure 1, and there we go.
Yeah, so this is figure 1. So this is our sky map of discovered fast radio bursts. So keeping in mind that these are fast radio bursts. Each one of these blue circles is a fast radio burst that was discovered in the sky. In this Mercator projection of the celestial sky, and so keep in mind so these were all discovered in basically a 1-year period from the sort of the day that CHIME became fully operational to a year after that in 2019, so this represents, this single figure has something like 4/5 of all fast radio bursts that have ever been discovered. So something like 100 fast radio bursts have been observed by telescopes other than CHIME, and there's 500 or so fast radio bursts here. Nice. And then there's 2 types of fast radio bursts that we discovered. So these blue circles, which are these non-repeating fast radio bursts. So really, these are fast radio bursts that we haven't seen to repeat yet.
There we go.
We don't know that they're not repeating, but we've only seen 1 burst from that location. And then the orange triangles are repeating fast radio bursts, meaning we've seen more than 1 burst that are coincident in both RA, DEC, and then this other parameter, which is called the dispersion measure. So the dispersion measure tells us that's the smearing of the pulse as it travels through plasma. So the plasma is dispersive through radio waves. Yes. And so what we get is a frequency-dependent arrival time, which we can measure at very high precision. Basically, that just tells us the column density of plasma between us and the source. Right, and so in order for a fast radio burst to be considered a repeat, it has to be coincident in both sky location, but also in column density depth in terms of plasma that we observe.
I'm with you. Yep.
This is that first big sample of fast radio bursts, and so there's a bunch of so this is what we've done is we've released a catalog of all these fast radio bursts to the community, and we can start doing astrophysics with it. So I'll first maybe I'll talk a little bit about what's in this catalog, and then some of the astrophysics that we've done so far, and then hopefully show you that you can go and download this catalog and do whatever you want with it, and if you have a wacky idea, then or not wacky idea, then you can go and go do your own thing. So what's in this catalog? So if we go, if we skip down to table 2.
Table 2. And let's get to table 2. Table 2, description of the data fields.
Yeah, so this is everything. So that for every fast radio burst, so all 536 of these bursts, these are all the things that we'll tell you about them. So there's 54 pieces of information here, but all the basics are there. Things like we have a transient naming server name. There's the RA deck and uncertainties in those, which very basic stuff. Things like we convert that to galactic longitude and galactic latitude. We have the localization errors, which are really important for us. So CHIME is a compact radio interferometer. So it's really good at seeing transients in the sky. It's not so great at localizing where they are in the sky. So the uncertainties in the location are typically quarter degree scales. So that's really important for using the catalog. But then beyond that is a bunch of information about the survey itself, right? Things like the exposure. For any given fast radio burst, for its location in the sky, we tell you how long that part of the sky was in our field of view, right? And that's it. That's really crucial for if you want to know, analyze something about the spatial distribution of fast radio bursts. You need to know how long that piece of sky was in our field of view.
Right. Yes, I'm with you.
Yeah. So then there's other metrics like the signal to noise, this dispersion measure, like row 18. So there's a couple different dispersion measures that we quote, though the one that was found in our initial search, and then a refinement later on using a piece of software we call FitBurst.
Yes.
And then measurements of brightnesses and a bunch of other properties like temporal widths, bandwidths, flux and fluences, and time of arrivals, things like that. So everything that we know about the fast radio burst, basically, we're telling you about the fast radio burst.
Good.
And so and so you have it all now if you want to use these 500 sources or so. If you can go run up to figure 4, I want to show you a little bit about that. Talk about exposure for just a second longer. So that's up, not down.
There we go. Figure 4 right there.
Yeah, that's right. So these are another sky map of where we discovered our fast radio bursts. This time in a more even projection that has sort of equal area. And you notice that they're sort of concentrated towards the North Pole. That just has to do with our exposure. So the color scale here is our exposure, right? So we see the further north you go, just because of our survey strategy, the North Pole is in our field of view 24 hours a day because we see southern horizon to northern horizon all the time, right? And so that's why we see just so many fast radio bursts as you go further north. But so this really gives you a feel for how the fast radio bursts are distributed spatially relative to how long we were looking at a given spot, and it's kind of pretty proportional, right? So
yeah,
I think intrinsically these are pretty isotropically distributed across the sky, and that our discovery rate seems to be pretty proportional to how much we looked at that spot in the sky. Okay, if you want to skip down to figure 6, I can show you some examples of how well we can localize these things.
Okay.
Yeah, so here's an example of 4 fast radio bursts and where we think they're coming from on the sky. And you can see the uncertainties are of order degree scale, half degree, quarter degree, for a given fast radio burst. So these are just probability densities of where they are, and then there's these multimodal localizations, and that just has to do with the interferometric beam that we form, and that adds this little bit of uncertainty in where each source is in the sky. So these are just 4 examples, but we provide this plot for all 536 FRBs that we've that we've discovered.
Very nice. There we go.
Okay, so let's actually look at some fast radio bursts. So that's figure 7.
Ooh, that looks like an FRB. Let's do the global, and then if you want to zoom in, we can plow in on 1 or 2 or 3. There we go.
Yeah, so these are what we call waterfall plots. So each one of these little postage stamp is so it's the dynamic spectrum. So each postage stamp is the brightness, the color scale is the brightness as a function of both frequency, spectral frequency, and time. So our observing band is 400 to 800 megahertz. And you see the time axis is measured in milliseconds, right? And so each one of these flashes, it's broadband. We see it over a range of frequencies, but can have a duration from between 1 millisecond and maybe 10 milliseconds, right? And so that's what each one, and so each one of these is showing you fast radio bursts. So this, I should say, this has this dispersion effect taken out, right? So normally these are very smeared out over time. So it's a millisecond long intrinsically, but But we actually see it arrive. It takes seconds for it to arrive at our telescope because the low frequencies arrive after our high frequencies because of this dispersion. But we've taken that out here. So we've relined up all the frequencies for our best fit dispersion.
Okay, got it. That's a 0 point.
Yeah, that's right, exactly. And so that shows, these broadband, and after you've done that, these look like very broadband flashes. They have a little bit of a tail, you'll notice, right? So there's this one side exponential decay, and that has to do with not from this dispersion, but from scattering. So that's from multipath propagation as the fast ray burst travels through inhomogeneous plasma along the line of sight. So that's giving us a handle on sort of the environment of the fast ray burst. And you see there's all these different morphologies that you see. Some are very narrow, some are broadband, some are wideband, some of them are bright, some of them are less bright. It's a whole zoo.
Yes.
But what gets really interesting is once you compare these, so these are all this is a sample of our one-off fast ray bursts. There's many more than you can see here. But when you compare these to the next figure, which are a sampling of our repeating fast ray bursts, you see the repeating fast ray bursts are a little bit more, the zoo is more exotic.
Yeah.
Okay? So notice how each fast radio burst tends to be more narrow band. It doesn't occupy our full 400 megahertz of bandwidth. Right. And the morphology of each one is just more complicated. Right, so you've got sometimes this downward marching structure. You get multiple bursts, and the bursts happen at different frequencies. There's an even bigger and more exotic zoo happening here than in the previous figure. And so that's actually one of the key conclusions of this paper, is that repeating fast radio bursts are different from non-repeating fast radio bursts in more ways than just the absence of repetition or presence of repetition, right? So repeating fast radio bursts, they repeat, but they're also just intrinsically different. They just look different than non-repeating fast radio bursts. I
have a question.
Yeah.
On repeating bursts, so if they repeat and they repeat and they repeat, is each family of non-repeatable burst itself repeatable, or when an object repeats itself, is it all over the place?
Yeah, so that's actually shaded colors in this plot. So notice how the first 11 plots here have purple shading and their top panels and side panels.
Yes.
Yeah. So those 11 bursts are all from the same source.
Yes. Got it. I see the naming convention here.
Yeah, there's a naming convention up in the top corner, which is a little bit too small to see here. But those first 11 are from the same source. The next 2 are from the same source.
Got it.
Or maybe it's just next 2, and then I think the next maybe 15 after that are all from the same source.
The green boxes.
The green boxes.
Yeah, I see. So to answer my own question, they're all over the place.
They're all over the place. Each one is its own. Each burst, even from the same source, just looks completely different. Sometimes they're bright, sometimes they're dim, sometimes they're high frequency, sometimes they're low frequency.
Yeah.
Wow. Every individual burst is its own sort of snowflake. If you will.
And of course, at some point, you're going to get more than 26 repeating bursts from one. And so then you're going to have to do sort of the, supernova game of A, naming convention. Very cool. Yeah, right. Nice. Thanks.
You're right. So, so actually, let's to quantify that a bit, if you can go down to figure 10.
Figure 10.
Yeah, so we do a series of comparisons between the sample of repeating bursts and non-repeating bursts.
Nice.
Right. So the first of those is figure 10, where we compare their spatial distributions. Now we have a lot more non-repeating bursts than repeating bursts.
Yeah.
Right. So the histograms are a lot bigger for the non-repeaters than the repeaters. But we compare all the different properties to see if are they consistent from being the same from the same population? Yeah, and for things like spatial location, the right ascension, the declination, the dispersion measure, as far as we can tell, small number statistics, but as far as we can tell, they're the same distribution.
Yeah.
Right? They're not intrinsically different.
Right, you don't get spikes over here, for example. Right.
Yeah, that's right. If you go down to figures 12 and 13, we do the same thing for things like signals noise and fluence and flux, right? So just how bright these bursts are, right? And again, there's no evidence these come from different distributions.
Yeah.
Again, we don't have that many repeat bursts, so we can't. There's not. We can't see really subtle differences in these distributions, but as far as we can tell, they're the same. Right?
Cool.
But what does change is once you go to the width. So figure 14, just down a page.
See that in the yes.
And we look at the width. So this is the temporal width.
Okay.
Okay, and these are just two measures of the temporal width. One's a fit and one's sort of a boxcar best fit, but they're just two measurements of the sort of the same thing. And here, if you do a statistical test, you decide actually that that these are actually drawn from different populations, right? The repeaters intrinsically have wider widths. Their duration is longer than the non-repeaters, right? And notice the logarithmic y-axis, right? So for the non-repeaters, basically all of them have a width of 1 to 2 milliseconds, maybe 3 or 4 milliseconds, right? And a small fraction of them have widths that are longer than say 5 or 6 milliseconds.
Yep.
Right. Whereas that fraction is much higher for repeating bursts. Right. So they're morphologically just very different. Right. So properties like the spatial locations and the dispersion measure and the brightnesses seem to be the same between these two populations, but morphologically they're different. Okay. And so we can do the same thing. So this is temporal width. We can also look at spectral width, which is then the next plot.
Figure 15. Spectral width. There we go.
Right. So or bandwidth. Right. And here, notice that the non-repeaters, something like 90% of the non-repeaters have a bandwidth that's 400 megahertz. Our entire observing band, right, occupies our whole band from top to bottom. Right. And then some other fraction of them, spread out and have different bandwidths. But for the repeaters, right, none of them occupy our whole band. Exactly 0 whole band. Right. And in fact, they tend to be fairly narrow band, have bandwidths of half our band, 200 megahertz, or even a quarter of a band, 100 megahertz. Right. So again, this is morphologically a fundamental difference between repeaters and non-repeaters that's very statistically significant. So it's just driving home and in a statistical sense that repeaters and non-repeaters are different in more ways than just the presence or absence of repetition. So this is, I think, sort of compelling evidence that there might be more than one subpopulation fast radio burst, right? That repeaters and non-repeaters might come from different physics, right? Now we can't know that. There might be a spectrum, of behaviors, right? Maybe a source that repeats more often is more likely to have a narrow bandwidth, right? It could be a continuum, but it could also be a dichronomy, and that we can't tell the difference between those. But it's certainly telling us that repetition has something to do with morphology in a very strong way.
Yeah, I'm with you. Very good. Very good.
Okay, great. Okay, so then the next thing, so that's a comparison between subpopulations. The other thing that we did is sort of an absolute population characterization, and for that we needed another tool. To deal with, so if you can go up to figure 9, if you want to talk about the population in an absolute sense, you need to deal with selection effects in some way. Indeed. And selection effects are just really, really, really hard to deal with. And so we had to figure out a way of calibrating our selection effects, and so what we did are called these injections. So what we do is in software we put synthetic fast radio bursts into our pipeline in real time and see if we detect them on the other end. And only a small fraction of those do we actually detect. Most of the simulated fast radio bursts are actually outside of our field of view. So we don't have a chance of detecting them, but but you know, we have this way of calibrating, you know, which fast radio bursts we're seeing and which ones we're not. Okay, and so that allows us to do the analyses that are shown in say figure 16, right, where we can look at selection effects for different properties and see, you know, are there what fraction of FRBs are we seeing? So we go to figure 16. So yeah, so figure 9 is it's just a schematic for how that works, but you know, it's a software, it's a piece of software that does the injections. But what that enables is our analyses like this, which is showing us the distribution of, in this case, dispersion measures in our sample, right? And so the left-hand side is showing the distribution of dispersion measures that we see. Okay, the top panel is showing what the selection function is in this space.
Yes.
And you see we're most sensitive to certain dispersion measures. We're actually less sensitive to low dispersion measures and to high dispersion measures.
Less so, but yeah.
And then when we compensate for that effect, that's the distribution we see in the end. And actually, they're not very different, right? Selection effects for this property aren't super important. This is that line of sight column of plasma, and it turns out selection effects they matter. They're order unity effect, but they're not bigger than an order unity effect.
Yeah.
Now you can contrast that to figure 17.
Yeah.
And so this is a scattering property that we can measure. Okay, so scattering is when there's turbulent plasma between us and the source, and that has another temporal broadening effect. It smears out the fast radio burst in time.
Okay.
And that makes them really hard to detect. And you can see in the very top panel what the selection function is, right? For unscattered bursts, we're highly sensitive, and then our selection function goes all the way to 0 for very highly scattered bursts.
Yes.
Okay? And so then the bursts we see in the bottom panel of the left figure, that's the histogram, right? And that's what the bursts we see. But when we compensate for these selection effects, actually we kind of, we infer that there's a lot more of these highly scattered events than we're actually seeing.
Right.
And in fact, you know, we're so bad at seeing really highly scattered bursts. They're just intrinsically very difficult to observe, that we have to actually have a very poor understanding for how many, you know, in the right panel, and once we compensate for selection effects, the error bars are just very big. There could be, you know, bajillions of these things, or there could be very few, right? In the right panel, you'll see that the histogram, has very big error bars on it. That's because you're taking a histogram that we've observed, and you're dividing it by a very small selection effect function. Right. And so that just blows up our error bars. So we think there might be a huge number of these highly scattered events that we're seeing just a tiny fraction of them.
Right.
So that's maybe telling us that a lot of fast radio bursts are just live in very turbulent environments where the signal it's just sort of obliterated before it makes it to us. It's smeared out to an extent that we can't really see it. Although the uncertainties are large, because, you know, those are the events that are basically impossible to see.
Right. And so the gray bands indicate you're ignoring those in the model fits anyway.
Yeah, that's right. The uncertainty is just too high, so we ignore them in the model fits. And so that model fit is just too, you know, it's just describing the sort of the main lobe of the population, but we don't actually know if that's all of the 90% of the population or 10% of the population, right? The gray band, you know, what's happening in the gray band is just very uncertain.
Got it. I'm with you.
Okay, and then the other thing that allows us to do, so if we can go down to figure 22 now. So the last thing the last technical piece I want to talk about is our measurement of two key properties of the FRB population. Here I'm showing just a histogram of the signal to noise.
Mm-hmm.
Okay, and then we try to fit that histogram of the signal noise to try to figure out what the brightness distribution of fast radio bursts is and the overall sky rate of fast radio bursts, while compensating for these selection effects using this injection system.
Okay.
And so we develop a formalism for doing this. And you see on the right-hand panel, those are our Markov chain Monte Carlo samples in this space, right?
Okay.
So the rate is the vertical axis, and alpha is this power law index for the brightness distribution, the cumulative power law index for the brightness distribution.
Yes.
So if the universe were not expanding, this would be exactly it would be exactly minus 1.5.
Yes.
Right. So that's for a Euclidean universe. And that's the expectation we would expect if most of the universe of most of the fast radiobursts are at lower intermediate redshift. You'd expect exactly minus 1.5.
Right.
And because in that case, the expansion of the universe isn't an important factor, and we get something that's fairly consistent with minus 1.5. And that's just because we're pretty sure the fast radio bursts we're seeing, they're around redshift 0.5. They're not at redshift 1 and 2 or 3.
Okay.
Right? And so the expansion of the universe, it matters, but it's sort of a subdominant effect here. So we get the sort of the brightness distribution you expect for a Euclidean universe. But remember, I told you we have this dispersion property that tells us how much a plasma is between us and the line of sight.
Yes.
So that should correlate with distance. The further away something is, the more IgM there is between us and it.
Yep.
And so we can subdivide our population based on this dispersion measure and see if you see different brightness behaviors for populations at different distances.
Yes.
And you expect that, right? That ones that are nearer by would have they'd have preferentially a different brightness distribution than ones that are further away.
Okay.
And so if you go to the figure 23, we're showing the posterior fits for the 3 samples, the full sample, and then the low DM nearby sample, and the high DM far away sample. And in fact, you do see an evolution of the brightness distribution that depends on dispersion measure.
Yes.
That's highly statistically significant.
Yes.
And so that's saying that we have this data set has information about the distance distribution of fast radio bursts in it, that this dispersion measure is telling us something about the distance. And actually what we're doing now is trying to model that in more detail and figure out exactly what, this 2-parameter space of brightness and dispersion measure is telling us about the cosmological distribution of fast radio bursts.
Right. Very good. Yes. Clearly. Okay, cool.
Okay. So I guess the last figure that we'll look at is, I guess, figure 25, which is a rate comparison.
Oh, okay. Figure 24, 25 rates.
Yeah, so this is the rate that we measure. So the 2 axes here is how many fast radio bursts there are over the full sky or each day. And the horizontal axis is just what frequency you're observing at. So first thing to see here is CHIME is actually the first survey in its frequency range. It goes from 400 to 800 megahertz, which is not where other surveys typically operate at much higher frequency or a much lower frequency.
Yep.
And we measure, a rate of about 1,000 per sky per day above some energy threshold.
5 Jansky.
Yeah. And that's actually a fairly high rate, but it's actually not incompatible with the rates that you see at higher frequencies, say, L-band 1.2 to 1.4 gigahertz.
Yeah.
And those are the other big surveys. It does seem to be incompatible with what another survey in Australia, Atmos, sees. And so we see a lot more fast radio bursts than they do, which we're not, that could just be differences and how we analyze our data and how we're compensating for selection effects. Here we think we've done a really good job of calibrating our selection effects to give you a realistic overall sky rate. But there's different conventions for doing this. But overall, there isn't strong evidence for a strong evolution of the rate as a function of frequencies. And what we get is pretty comparable to what Parkes and ASCAP see at higher frequencies.
Okay. Yep. Roughly 1,000-ish.
Yeah, roughly 1,000-ish per sky per day.
Yeah.
And you'll notice, I should brag a little bit, right, that we have the smallest error bar fractionally, just because we have by far the most fast radio bursts and the biggest field of view.
Got it. It's the width. Yeah, I'm with you. Yep.
Right. So that's, I mean, I think that those are like the take home messages of, that's the analyses we've done on this, but really the big data product here, the big point of this paper is not just what we concluded from the catalog, but what you can conclude from the catalog, right? All this data is public. Everything that we know about a given fast radio burst, you now know about a given fast radio burst. You just follow the links in the paper and go and download them, and you can have it. And so anything you want to know about the population, if you have a way of analyzing it, you're very, very welcome to do that. Yeah.
Okay. Very good.
So I guess just to look forward a little bit, so this is our first catalog. It's our first year of data. And there's 536 events in that catalog, which we think is a big accomplishment. However, the cutoff date for being included in the catalog was July 2019.
Okay.
It's now, as of a couple of days ago, 2022, and Chime's been working beautifully in that entire time. So there's a lot more data to come, a lot more that we'll be able to do with this data set, and a lot more you'll be able to do with the data set once we make those public. So you should continue to expect that the number of known fast radio bursts will just continue to grow very rapidly. And then the other thing is that the quality of our data, what we know about each fast radio burst is going to get better, right? So we're discovering more fast radio bursts, but we're also just getting better at analyzing each burst. The properties we measure from them will be better. And then the really exciting thing is that we're adding new instrumentation to get even more information. So our biggest weakness is those localizations, right? Yeah. Quarter of a degree on the sky. Because of that, we can't identify hosts for the most part. We don't know which galaxy a fast radio burst is coming from. Therefore, we can't get redshifts. It's really we can't get environment. It really limits what we learn about fast radio bursts and what we'd like to do. And that's because we're a compact interferometer, right? We don't have high spatial resolution.
Right.
Right now, we're working on this effort to add these outrigger telescopes. So these are VLBI mini versions of Chime. They'll be situated all over the continent.
Cool.
And we'll have VLBI localizations for every single fast radio burst. So we'll know where every fast radio burst is on the sky once these turn on to 50 milliarc seconds. And so then we'll know the galaxy, and then we'll know the redshift. We'll know the environment. We'll know so much about these fast radio bursts. So we're really, really excited to sort of open up the fast radio burst data space yet again when we have that added crucial piece of information.
Mm-hmm. Very cool. Very cool. I'm looking forward to at least the next couple of years, if not the next decade, on some new Chime results and what they tell us about these FRBs. Reminds me of periods when GRBs were sort of in a similar, what the heck is this? Look at all this. And so we're sort of in that mode, but for FRBs. So very cool.
That is something, an analogy that's been made to me, I think, a dozen times over the last couple of years. I think it's very, very nice to be in one of those phases of a field. It's really discovery mode. It's very cool. Very nice. All right, Kiyo. Thank you so much for walking us through the very lovely Chime first radio burst catalog article. Thanks. Thank you very much. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.